Okay, thank you everyone for joining us. This is Unlocking the Secrets to Fractured Bedrock Injection. This is part 2 of our ongoing webinar series here. If you joined us last week, we talked about fractured bedrock characterization using an RDC process. If you weren't able to join us or you'd like to revisit that, those videos will be available on RPI's website here shortly, www.trapandtreat.com. And then you want to click on the videos or video library section. Either link will take you to those videos. So we're going to expound upon what we talked about last week, but I want to start with a thank you. We can't do these alone. We have a lot of help. RPI, AST collaborate a lot. We had some help from AIPG as well this time around, and also the Kentucky section specifically, where Bill is one of the officers there as well. In terms of where we're going with these webinars, again, this is part 2 for the Bedrock. Part 3, which we're including in the Bedrock, is next Thursday, same time, same channel, same registration. Links are up on our websites. That will be focusing on the pre-drill methodology. So if you joined us very early on in this process, we focused on some overburn applications, some chemistry technology applications. Then we moved into Bedrock. And this last one's going to be the bridge between the bedrock and the overburden component, what to do in weathered or less competent bedrock. So our colleague Mike Mazzarese will be hosting that next week. So as a corollary to these other 2 bedrock presentations, that's another add-on as well. Something you're going to see this week, we've got polls. We'll do them on slides 11 and 29. If you need to ask a question, there's a question box there in the control panel. There's also a chat window as well. If you need a certificate of attendance, please reach out to Bob and we'll furnish that for you. Real briefly, for those who haven't joined us on a previous webinar or last week, this is kind of the RPI group tripod. RPI is the developer of the chemistries we've talked about in previous presentations. We'll show you a case study of an implementation of that in Bedrock here today. AST, we are the distributor for those technologies. We're also the design arm. So regardless of whether you're working with one of our authorized installers or directly with AST or RPI, we'll be involved in this process as well. So this is a fully functioning quality control unit within the RPI group. So we put forth the best designs and achieve the most success on site. So this is a little different than other providers or vendors out there. A little bit about where we've worked. Don't think things we've talked about last week, this week, in earlier presentations only need to take place in the lower 48. Many of you on these webinars have joined us from international locations around the world. We've got a footprint there as well. So these technologies and systems will travel. So if you have something, in this case this week, fractured bedrock, that you want to discuss that doesn't happen to be just around the corner from your location, let us know. And lastly, before we move into our review, I just wanted to show, for those of you who couldn't join us last week, this isn't all encompassing, but this is a good body of work that we've established to date. Dates back to 2011, really started to expand in 2013, 2014. We're looking at sites here in red that have achieved NFA as example. The blues we've either completed as pilot or they're pending full scale. Here's some full scale completions and some other work as example we have coming up. So a lot of these are varied locations, varied geologies. They're typically petroleum hydrocarbon or CVOC contamination. Again, if you didn't join us for the RDC last week, we talked a little bit more about how to characterize these sites and these geologies. And now we're moving into the injection side, but this is just a revisit to, yes, this works extremely well in fractured bedrock, and it's because of the process. So here's our roadmap for today. I'm going to briefly revisit the RDC because that's how we move into the injection design. We're going to talk about the injection itself, geology considerations, how we actually get material suspended and flowed into fractures, features, secondary porosities. And once those have developed, how you sustain them. These systems are not off the shelf. They're custom packers, custom pumps, and they take experience and knowledge on how to run them, which our group certainly has. And Bill's going to transpose that into an in-depth case study. at the end of this to show you an example of how this all comes together from this week and last week. So a quick revisit here. Today we're focusing on the implementation side of this. This is kind of the approach, the trap and treat approach to any site here with a focus on fractured bedrock. So this is going to move into the design or redesign and then implementation injection. So here's our first poll question. For those of you that are joining us for LSRPA credits, we'll need you to answer these. Let me launch this one here. So our first poll is, have you previously performed a fractured bedrock injection program? I'll leave this up for about 30 seconds and we'll share the results. All right, we're over 75% voted. I appreciate that. Okay, last chance to vote. Yes or no question. All right, I see 90% of you have voted, so I'm going to close the poll here. I think I can share it. So here's our poll results here. So about a third of you, a little more than a third of you have done a Bedrock program before. That's great. Hopefully we showed you some interesting stuff this week and last week to help you with those processes. For those of you that haven't, again, there's a question and a chat window. You can ask questions at any time there's this presentation, and we'll address those at the end. Okay. So a quick revisit to the RDC. Again, this is our roadmap. This is our approach. I'm going to start with actually revisiting what is a fracture, what is a feature. There's different types of fractures and features in any drilled borehole that we're going to run into. They could be naturally occurring. They could be man-made, from the drilling process. All these features are important to us. Going back to the geophysics we discussed last week, we're looking for the areas where we believe, depending on the contaminant, where they may have propagated into those features, fractures, contact zones, secondary porosities. And again, doing that RDC process allows us to evaluate if it resides in that zone. So as we moved last week through the geophysics, the borehole geophysics portion of this is a very, very important component when we move to injection, because that's where we select our zones. And in some cases where we may not have favorable areas or zones, or maybe we don't have a lot of features or fractures, or they're very tight, undeveloped. Maybe we have a lot of secondary porosity. Those are places where, as Bill mentioned in his example last week, we're going to walk the packer up and down the hole in a pilot phase potentially, or if it's a small scale, small site, a full scale phase as well, trying to determine where we were unable to determine through those processes, geophysics and discrete sampling, if there may be ability to inject. So we'll focus on that in an example coming up. And again, why is all this characterization important? Well, your transport feature may not be as clear cut as this example here. There could be different flow paths. Obviously here we're showing varied topography, so identifying the depth, if it's along a specific contact, a specific bedding plane, a specific fracture network on the site. All this characterization becomes important because when we put the injection packer down hole, we need to know where to target those zones. So this is a very simplistic model of a site here, but this was a site that our Kentucky office did a couple years ago, and that green highlight there identifies the bulk of where the contaminant mass was flowing in the fractured bedrock at this site. And again, with the RDC process, really we're tying everything together. And this is a real snapshot of what we talked about last week for those of you that couldn't join us. But it comes back to the geophysics we discussed. It comes back to a discussion with you, our clients, the regulators you're working with, coming up with a RDC process that augments your current CSM or develops a new one, either specific to a portion of the plume, specific to a source area, All this is important data to catalog, review, and then subsequently use for your design. And really, at the end of the day, this sets expectations. Um, Unlike overburden sites where you can move over and continue to probe, you don't have that ability here. So going through the RDC and selecting advantageous places to put your boreholes, selecting advantageous or specifically characterized intervals to do injection is extremely important. So again, I just want to emphasize last week's presentation is a very important piece of today's presentation. So when it comes time to inject, what are we looking at? Well, Bill showed you this example of our various packer setups last week. I'm coming back to revisit it because really the characterization, discrete interval packers we use for characterization at a fractured bedrock site are very similar to the ones we use for injection as well. We typically call those our sister packers. There is a little bit of difference between the two. You can see the injection packer there in the middle has a yellow shroud around that. I'll discuss the reasons for that in a couple minutes. But really, as an example here on the left, we're looking to take that straddle packer downhole attached to our injection truck, which we'll talk about, and we want to look for these fracture zones, right? As an example here on the left, there's at least 5 significant fracture zones we want to target with that straddle packer in that 25-foot interval. So these are places where we want to, again, starting at the bottom up, and work our way out of the hole for injection. But there may be cause at this site or another site to do, again, walking the packer up and down that hole, injecting if there's secondary porosity concerns. So this packer equipment is really the heart of the downhole system. The injection truck is really the heart of the above surface, what we see most of the time system. I'll show you that in a few minutes. But again, these are very important tools that were custom built for us. You know, these packers here have 2 separate bladders that inflate uniformly and allows us to seal that borehole off. So again, what we're showing you here is not off the shelf. This is custom. A number of our employees have worked hard to develop these over the years and improve upon them with each subsequent iteration. So let's talk about the injection. That's what we're really here today to focus on. Again, think of this as strategic fracture isolation, injection, and remediation. The first thing I wanted to show you here is a slide that I use a lot, regardless of whether this is overburden or fractured bedrock or transition zone injections. And what we're looking at here is differentiated geology. And regardless of where our contaminant lies, as we identify the zones where it does reside, we need to make sure we're maximizing distribution. You know, we need to increase contact. Site remediation, regardless of setting, is a contact sport. So that RDC process we've discussed thoroughly. Again, this is where we're optimizing our product placement. So a lot of times with conventional downhole equipment, you may be, pumping into an open borehole. You may be trying to tremie the media into a specific interval. Even if a drill or other providers using packers, they certainly don't have the type of pump we're discussing here today. And without that triplex pump, which I'll show you here in a few minutes, it's going to be very hard to propagate your reactant into those zones and achieve distribution and treatment. So using that packer, we eliminate a lot of those drawbacks. This isn't open hole pumping. We're going to focus on narrow intervals, and we're going to make sure that we get development of that fracture feature. And if we can't, we're at least going to know that, if we can't force reagent into that interval, then there's a very low likelihood that a contaminant did as well. So here's a look at the triplex pump. This is our custom truck, custom pump setup here. On the right, that blue pump there, that's our triplex pump. That's attached to our Kenworth T800 truck. And as you can see in the picture on the left there, we've got a batching trailer as well. In this picture here, we're actually using it for a overburden injection that was on larger 10-foot centers. We needed greater distribution because of depth, so we actually took the Bedrock truck out there for this. So it can be used in that application as well, which is why I included this slide. This truck's not just specific to Bedrock. It does have some other applications. However, this is a fairly typical setup with the Kenworth there, the batching trailer, and the support truck as well. In terms of what makes the triplex pump special, It's a 3-piston pump. It's typically used for industrial or unconventional gas applications. It's 165 horsepower positive displacement pump. And the best thing about it is it runs off the PTO from the Kenworth. Um, and that's important because, as I'll show you in the next slide, that allows us to vary our flow rates um, in the subsurface, which is extremely necessary when you start to propagate some of these fractures and features with either fresh water during your freshwater test or subsequently reagent in your injection phase. The reason the trailer is there is that's our batch trailer. That allows us to continuously circulate and suspend product. And then when it's ready for downhole injection, we can transfer it over to the triplex to force it downhole through the injection packers. Here's a bit close up. This is the back of the truck here. What you're looking at here are the system controls and also the data logger. We put transducers and sentinel wells around the injection well or the area we're focusing on. That data can also be displayed or cataloged here as well. There are reels in the back. Those contain our hoses, both for airlines and injection. And there's a storage unit under the back of the truck there for our straddle packer setup. You can see here, one of our employees is using a wireless headset to communicate with the other employee who's focused on the borehole itself, so they don't have to, walk back and forth. They can use hand signals if they need to, but the wireless headsets allow them to effectively communicate even in noisy environments through noise canceling. So going back to that PTO comment and the triplex pump and how it couples up to the Kenworth truck, again, we literally call it switching gears because that's what we're doing. If we need to vary the RPM, the speed entering that pump off the PTO, we can change our flow rate very quickly. Allows us to give us a wide operating range, which is necessary for varied geologies, areas we're exploring, not just features or fractures, but secondary or tertiary features in the borehole. And this gives us great flexibility as we move up and down the borehole on site. So here's a brief look of what that triplex does when it's hooked up to a directional tip. Now, again, this is not the straddle packer setup. This would be used for overburden, but we're looking at various flow rates here as an example. And you can see as we, again, shift gears, change our flow rate. Again, this example here is 20 to 250 GPM. You could see the power of that pump. Now, I want to temper that comment with that power is useful, but we also want to control it, right? With great power, power comes great responsibility. And we'll talk about how we manage that here in a second. But it's also important because we need these flow rates to achieve distribution. At some sites, we're not looking, for the low end. We can get 20, 30 feet of ROI. At some sites, we've had as much influence as 100, 120 feet away. But our typical designs are going to be somewhere between 40 and 60 feet between the injection boreholes. So we need that power behind us to continue to propagate the injection material into those features or fractures that we're working with. So here's a brief video, again, focusing on that 250 GPM flow rate in the last slide. Just kind of shows you the power, the force behind that pump. This was done at our Kentucky headquarters as an example. And this other video here, we're focusing on that shroud we talked about a few minutes ago. So while we showed you the power of this pump, we talked about how it's versatile. And you can see here we've got the straddle packer inflated and the shroud attached. We want to control it. We need high flow rates, but we need gentle flow. We're not looking for a pulse, a very forceful event. We want to create a flooding. Not so much like a beach wave crashing, but think kind of like a flooding event in the subsurface that fills up that feature, that fracture, allows us to increase pressure for either a freshwater test or subsequent injection on it. So that you can see there's the 18-inch interval. We increase the pressures there. And again, we talk about pressures. There's system pressures, and then there's tip pressures or packer pressures. And Bill will explain that a little bit more here in a second. But again, I think this is a nice example of what this actually looks like in the borehole. from a display standpoint. So, Bill?
Yeah, online, can you hear me okay, Derek?
I can hear you.
Great. Thank you for the lead-up introduction here. And thanks for everyone for taking the time out of your busy schedules to join us today. So I'm going to take over from here and talk a little bit more about the pump itself and then the case study that's coming up. I believe we have another poll, though, Derek. Is this the slide for this?
I think it's coming up here in a couple slides.
Okay. So we'll get into a little bit more about the geologic materials and some of the questions that come up about the material that we work in. And definitely want to go back to Derek's reflection earlier about recognition and a moment of thanks for the folks that are involved in the webinar series, but also in the development of our technology over the years and where we are today. Mr. Ray Boyle out of our Colorado office is the foremost authority in developing this piece of our technology and walking us along through this as we've grown and learned ourselves. And where this injection system came into play many years ago was actually from the water well rehabilitation industry. Ray is located in Colorado, and his business that he developed early on was for the purpose of increasing permeability from low yielding wells that had essentially deteriorated with time. And so his hydrogeologic background had come into play with assessing all kinds of rural and remote areas of geology within Colorado, and using a injection system that could reinitiate some of those permeable zones that were present within an existing well, and could rehabilitate that well to a point where it was having a nominal yield for water production for domestic use. And so these next couple of slides we're going to go here is a composite, so to speak, of all of these historical geologies, both through the water well industry and through the remediation work that's been done at AST, that we've compiled together, looking at what he's calling here formational resistance of geologic material. And so your y-axis here is essentially your number of cases that are in the poll here, or in the representation graph here. And the formational resistance factor is this PSI per GPM. And so, as Derek kind of talked about earlier, with the variable speed and flow, variable speed of the motor allows us to have varying flow rates and varying pressure capabilities with this pump system. And this is really important. We're going to get to that in just a moment. In being able to work with these different geologies and actually achieve proper distribution and reach within a formation. And what we've got here is if we look at the graph, again, we're looking at several types of geologies compounded into a common graph here, coloration scale. But what I really want to show here is the lower numbers that we have off to the left-hand side is where the largest distribution of these instances where we actually achieve breakdown within the formation and we're able to propagate out within the formation itself. And so this formational resistance factor number is just for visualizing this on a normalization curve because of how varied the data is between flow rate and PSI. So you have to find a way to normalize it. And so here what we want to do is just keep in mind, looking to the left-hand side of this, that the bulk of these sites, or the bulk of these geologies, are going to respond with these lower numbers here that, you know, have an upper limit of about 50 psi per gallon per minute. So next slide, Derek, please. So now we're going to sum all of the materials together under a common composite, so to speak, so that we can see these in individual bars. And again, just another visualization to show us that this skewing of this particular breakdown, or this formational resistance number, out of 445 data points that we use to come up with this graph, tend to fall on this left-hand side of the graph. And where I'm going with this is that when we do these types of injections, Derek hit it pretty hard and covered it pretty well, but I'm going to say it again. is that we're working with existing features and porosities within the formation itself. We're not creating new factors. We're not trying to break the rock itself and actually inject into new material. We're utilizing existing pathways and flow paths that would be both your transport zone for groundwater and, more importantly, in contaminant remediation, the contaminant itself. So what we're trying to do is take advantage of that. So that's why the upfront RDC work, looking at the geophysics, looking at the pumping test data, helps us to better target these zones where we can take advantage of those features that are already existing within the formation. Next slide, please. So this is, again, comes back, we're now taking the gallon per minute out and just looking strictly at PSI here. And so looking at where typically in most of these scenarios where your breakdown pressure occurs within a specific feature tends to be along the lower side. Again, we're not trying to frack rock, we're trying to essentially just take advantage of existing porosity within the formation and permeability. And what we see here is what we typically target when we do an injection is initiating a freshwater test on those intervals. And where we kind of assess a go or no go on that specific interval is initiating fresh water. And if we reach that upper limit of about 1,200 to 1,400 PSI and nothing happens, it just holds, that particular interval is believed to be non-producing and non-effective for the purpose of injecting a slurry. So using this as kind of a metric for us lets us know, where we can hope to achieve breakdown and initiate propagation of both water and then eventually a slurry density that's going to be inserted or implemented into that specific feature. And again, we've got this leftward skew. We're not getting up into these insanely high pressures that require this. The majority of this is going to be somewhere around that 400 to 800 PSI range on average in most cases. Next slide, please. And so this is the big important slide that I like to talk about here that really illustrates this for everybody. Again, we're going back on a y-axis here, looking at PSI per GPM, looking at that formational resistance on a particular borehole. This is real data from a site, I believe, up in the Northeast. And if you attended last week's webinar, there was a borehole camera video that showed this specific feature here in the image on the right-hand side at 59.2 feet below grade. And this doesn't look like it's a significant feature other than we've got some staining on the side walls of the bore and what looks like fluid flow coming out of that specific interval. And what we're showing here on the left-hand side graph is the progression of injection at the specific borehole at this specific interval. And so the initial injection that shows 34 GPM at 1,200 PSI, this is where we're initiating a freshwater test injection on this borehole and trying to see if we initiate breakdown of that feature and can actually get water into that interval. And we see that at 1,200 PSI, we do get breakdown and we are able to initiate flow into that zone and continue with ramping up. In this case here, the small 25 GPM pump was incapable of doing it or had limited flow. So we're actually switching over to the triplex itself. And this is, again, using that variable speed, variable gear progression as we go. And as that breakdown occurs, we drop off on the PSI, but we have to ramp up our gallons per minute in order to further propagate out into the formation. So as we reach over at data point number 6 here, we can see that by the time we're finished with injection, just fresh water alone, we're at 72 gallons per minute, 700 PSI reading into what it takes to get into the formation itself. Now the next bars that we have above this is when we switch over to slurry injection. So now we're adding a solid particle in a suspension of this material in the water. So now we've got a little bit of a different material that we're working with here that we have to deal with. So switching back in, we now are at 35 GPM and we're at elevated PSI of 680. But as breakdown is initiated and that material beginning to propagate out into the formation, we progressively have to increase both our flow rate and the pressure continues to drop off. So we may keep bumping up our flow rate in order to maintain a steady pressure on the formation as we're propagating out. And so then where these 3 data points end, that's a batch followed by the next kind of grayish colored one there in the middle that says 72 GPM at 800 PSI. Now we're up to a higher flow rate, sustaining that upper elevated pressure of 800 PSI. And then as we get to that green set of data points at the very end, we can see that back at that 34 GPM where we've developed that specific feature quite well, we're down now around 200 PSI, but we need to ramp that gallons per minute up in order to sustain pressure and flow to continue to carry that slurry out into the formation. So by the time we're finished with this specific series of injections, you're looking at 72 gallon per minute at a lower 500 PSI compared to where we started initially at 1200 PSI just to initiate flow within that interval. And so just for the audience, typical volume of Voss slurry installed during each injection at the site was somewhere around 150 to 200 gallons by each of those individual data points that we see there that are on the graph here. Next slide, please, Derek. So poll question number 2 coming up. I'll let Derek take over with that. Unless you want me to keep going with it, Derek. What contaminant is most common at your fractured bedrock site or sites? Give everybody a minute to look at that and vote. Looks like we're about 79% voted thus far. Give everybody a few more seconds to vote. All right, so we have the distribution here of the polling that went on. So it looks like we've got a close to even split between petroleum hydrocarbons and CVOCs. Excellent there. Thank you for answering that. The next slide we've got is going to be, a series of slides is going to be a case study. So walking into our case study showing an actual implementation of this technology and methodology involves a former dry cleaner here in Central Kentucky. So for all you CVOC folks that are on the call that answered that poll, this is right up your alley. Location here in Central Kentucky. History on this site for me is I started working on this when I came on board with AST. This is where we were actively working when I first came on board with them in 2011. The actual site use is a retail shopping center. Geologic settings in are bluegrass, and the bedrock is an Ordovician limestone overlaid by clays, silty clays. And as we can see here, Derek, can you enable your pointer dot for me, please? Great. So as we can see here, behind the dumpster with the open door looking right at us in the center of the photo, the building directly behind is where the dry cleaner was formerly located. And you can see the adjacent facility next door where you have the people standing out back is a fairly busy restaurant. And the shopping center, this is in the back part of the shopping center adjacent to a stream. Very busy, very tight, small area to work with, as we can see here. Our injection system that you've seen in the photos before is off to the left-hand side here, just off camera. But you can see that mixing trailer that Derek had mentioned in his earlier slide present there right at the tail end of that photo. Next slide, please. So conceptual site model facility, again, the primary COCs here are PCA and daughter products. Groundwater impacts were identified in both the overburden and in the limestone bedrock. All overburden soil and groundwater sent from the top of groundwater of 6 feet below grade to the bedrock interface at approximately 10 feet. And the overburden impacts were on the order of approximately 3,000 square foot. Limestone bedrock groundwater impacts extend from the interface to approximately 20 feet below grade. And the groundwater concentrations range anywhere from 400 ppb up to 87 ppm of perc in groundwater. Saturated soil in the overburden concentrations ranged from less than a ppm to as high as 500 ppm, and those highest concentrations were actually located at the soil bedrock interface. Here at the scale figure on the right-hand side, I want just to call out the two cross sections we're going to be looking at in the next two slides to further discuss this conceptual site model. Next slide, please. So looking at the left cross section that we saw in that photo, which is roughly to the north, the map we saw to the last slide, north is to the left of the page. Here on cross section 8A prime, identified through the geological logging and follow-up assessment work prior to the remediation, identifies a mature epikarst located and identified during the installation of monitoring well 1 and monitoring well 2 construction, as we see here in the central part of the cross-sectional view. As we move to the south to cross-section B to B prime, which is the next slide, Derek, please. So what was identified here, or was shown, was that the epikarst was not really all that prevalent here, or was not identified at all. And this was correlated through soil borings, or excuse me, monitoring wells 3, 4, and 5. So we do have a little bit of a transition zone located within that central feature along the source zone and flow path that we identify through the conceptual model. Next slide, please. So looking at the actual RDC results, again, RDC stands for Remedial Design Characterization. This is the assessment that comes into play to fill in data gaps and try and shore up the existing conceptual model so that we can refine the injection design and be more effective with our installation technique and distribution methods. And again, we talked about this weathered zone and this transition zone to the east of IP8, which had varying thicknesses and significant water with the highest concentrations at IP4. IP6 and 7 contain significant concentrations within the weathered zone, and evidence of that trough we identified in cross-section 8A prime, and a direct connection between IP4, 7, and 6. Small fractures below the weathered zone east of 8 produce significant water. So once we get into that confident zone with within the transition zone, there was a significant amount of yield from the groundwater within that system, and concentrations were greater within those fractures between 16 and 20 foot below ground surface than they were in the weathered zone itself. And newly installed MW6, Derek, if you don't mind highlighting that with your pointer off the left-hand side of the figure. This well was interesting because it was believed to be up gradient of the source and groundwater flow path, and was installed as essentially a control point, but indicated that there was significant PC mass and was believed to also be connected to the source through the lower fractures below the weathered zone. Next slide, please. So the remedial goal for this site, because of the facility type and the situation of inaccessible source mass located beneath the structure, managed closure was selected by demonstrating that significant reductions in contaminant mass in overburden, both soil and groundwater, had to be shown, and shown that it had been reduced and contained. The bedrock groundwater plume had to also show a significant reduction in size, and demonstrating overall a downward trend in contaminant concentration through long-term monitoring had to be demonstrated as well. Next slide, please. So 9 bedrock points were selected for the installation of the material, BOSS 100, at this particular injection plan. Number of injections and slurry densities varied across the site and based on each borehole and vertical interval that was initiated within each point. So utilizing the different CVOCs depending on PC and vinyl chloride as the dominant contaminants concern that drove the design. Looking at the aperture of each fracture that was identified through geophysics, downhole camera, and pumping tests, using that as a way to estimate the total volume of groundwater needed to achieve proper distribution within each factor or fracture. And finally, safety factors to allow for considerations of mass that may still be present within the system, or certainty of the data. Safety factor of 1.25 was used on 8 of the 9 points used for injection, except for IP4. This was given a safety factor of 3 because of its proximity to the building itself, and to account for any mass that may bleed out over time from beneath that building. Next slide, please. Excuse me. So getting into some of the results and data over time. Again, this remediation project was initiated in 2011. So the benefit is that we've had almost 10 solid years of data that we can look at to show progress of this managed closure and the success here at the facility. So what we're doing here is looking at the on-site wells on the east side of the creek, the stream, which I don't know if it was clear from the previous drawings, but that stream is going to basically go from left to right across the bottom of the page here, from MW2 to MW3 box that you see right there. And what I want to highlight here is going to MW6 on the upper left-hand corner. That's that well we kind of called out earlier as being a surprise during the RDC, that it was intended to be a control point for the purpose of defining the site to the north of the source area. But we can see during the RDC in August of 2011, we had significant perk impacts and daughters products all the way down through vinyl chloride in those samples. But we could see at the current sampling date of June 2020, we've maintained throughout the history of the remediation low-level detections or non-detections within that well. Source monitoring well number 1, located in the center of the page, looking at prior to injection 12 ppm of perk and ppm concentrations of daughter products. And again, looking at that managing of mass, we see that even 10 years after implementation, or 9 years in this case after implementation, we have continued reductions and shows a overall downward trend throughout the history of the site. And we can see from periphery wells as well here, MW2 at the creek, at the edge of the creek, looking at ppm concentrations coming down from the initial sampling down to low-level ppb concentrations, nearly meeting the MCL in cis and vinyl chloride. Next slide, please. Now we're going to move across the stream here. The figure shows us clearer where the stream is in relation to the site, which is up to the top of the page here, which would be to the east. What we want to show here is that monitoring well 103 and 101, located on the left-hand side of the photo here. We're getting impacts in them right around the time of the implementation of this technology. And over time, as we move forward to the current date, we can see that the MCLs are being maintained within those respective wells, and showing that any further contaminant migration from the source area is being halted and no longer reaching these particular locations. There was no remediation, I want to further add, on this side of the stream. So everything you're seeing here result-wise is occurring from treatment within the source area itself. Next slide, please. And a couple graphs to finish us out here, just looking at total CVOCs within 4 key wells that we looked at. Monitoring well 1, the blue line is the source well that we looked at that started off at least with the data table before at 11 ppm, but pre-data point we can see here that was taken earlier than the RDC from the client's data, shows that it was up in the 16 to 17 ppm range. Monitoring well 2 at the proximity of the creek, red line. And then the 2 100 series wells that we saw, 106, the purple line, which was supposed to be upgraded, and 104 is between MW1 and MW106. And as we can see here, just a global overall trend of knockdown, reduction, but then maintaining for many, many years after the implementation. And final slide here just again supports our contaminant destruction, talking about the trap and treat products. They are trap and treat. So they're going to be a sequestration using the activated carbon, but then we also have a treatment mechanism that's built in for the purpose of destroying the contaminants. And we're looking here again at monitoring well 1 within the source area, significant chloride, ethylene, and ethane generation all the way up through 2017. We do have lower numbers at this time, but if you recall looking at the data, we have a significant drop in CVOCs. So less CVOC to degrade, less chloride to generate, less ethylene and ethane to generate as well. So not unexpected to see that these numbers are lower as well, but they are in fact still being generated and showing that contaminant destruction does continue to occur even 10 years after implementation. And with that, I believe we're to the end of our presentation and ready for Q&A. My contact information here, Derek Pizarro, my colleague with AST, and then Bob Elliott at RPI is available there. Please check us out on AST, or follow AST and RPI on LinkedIn. And with that, I will transition over to Derek to run the Q&A.
Thanks, Bill. Again, please use the question and answer portion of the GoToWebinar there in your control panel or the chat. We'll receive both. I've got a number of good questions here already. So while we start to field some of these, if you have a question, a comment you'd like us to address, we'll bring those up now. If we don't get to every single question, then we'll follow up with those individuals specifically to their question after this event. So Bill, I'll let you take a quick break there since you've been talking, and I'll address the first question. It goes back to something mentioned at the outset of this presentation. How do we address weathered bedrock units? Well, can be a complicated question. Coincidentally, we have a great presentation next week that will address weathered units, less competent formations, transitional zones at the bedrock interface. Our colleague Mike Mazzarese is putting that on. You can register at the Trap and Treat website, trapandtreat.com. But real quick, the systems we discussed here today and last week, we're not going to use most of that equipment, or in some cases, any of it. When we get a weathered unit, we're going to use something we call pre-drill methodology, and that involves using augers or sonic rigs to reach the top of competent bedrock, stop at that interval, and then complete that borehole with hydrated bentonite pellets or chips. And then that bentonite column in that borehole allows us to go back through it with a DPT rig for injection. And in some cases, we may use the bedrock truck, but we may not need to. So that's how we access that transitional or weathered zone there. There's a very comprehensive presentation next week that'll cover that. So I do suggest you sign up and join us for that. If not, again, reach out to us individually, and if it's site specific or otherwise, we can answer some more questions about transitional zone. Bill, are you with me?
Yes, I'm here.
Okay. You all right if I lob a few of these at you too?
No, go for it.
All right, let's start with an easy one. What is the max flow rate and GPM of the triplex pump?
300 gallons per minute.
How about max pressure?
Max pressure is around 2,500 psi.
Okay. And just to reiterate.
Just to reiterate that, and maybe you're going to say the same thing, is the pressure we deal with is mainly to get through the system and to initiate breakdown of the formation. So most of what we see from injecting does not reach that upper limit.
Okay. First question here related to the process. Can your freshwater testing methodology in the subsurface rehab wells that are heavily sedimented in?
Yes, that's actually, so let's take a step back. The answer is yes, and that's where the discussion about how this system was developed and why it was set up the way it was back to the domestic water well industry. And that's actually how rehabilitation occurred, was utilizing fresh water for the purpose of cleaning out and rehabilitating these wells. And again, we're talking about open boreholes here specifically. I believe Ray may have had a capability of working with steel case wells or things like that in the past, but specifically for remediation, we're looking at open borehole wells, not cased wells. To get a little more specific about the freshwater question in the instance of remediation here, the typical freshwater test we utilize utilizes a smaller triplex unit. It's a small Caterpillar pump that's capable of an upper limit of 25 gallons per minute, but it does have that upper PSI rating that we're looking at around 2,000 PSI, if I'm not mistaken. We can do a standard freshwater test with the triplex itself, but we typically reserve the injection or the pumping work with the triplex to be strictly slurry injection. But as we showed in the extended graph that I showed with formational resistance, the freshwater test was actually initiated and sustained with the triplex, the larger triplex unit itself.
Great. Similar question. How do we typically assess radius of influence in a fractured bedrock setting? And does that estimate change based on bedrock, fracture network, or other variables? And how do you estimate that at the outset?
Yeah, it's a good question. The majority of our distribution verification is by the use of transducers and monitoring the surrounding network as we're working. Part of this comes down to the RDC itself that we talked about last week and briefly mentioned during this presentation. Prior to putting anything in the ground, we want to try and get a handle on what that reach is that we can achieve based upon a particular borehole, and taking that data into play and modifying it as needed based on what we see with going the other direction, actually trying to reduce fluids in the formation. And this is not a static plan. When we go to the field, it's not uncommon and actually quite regular that changes and decisions are made on the spot based upon what we're seeing in real time. So the way we do this typically is looking at hydraulic changes within surrounding monitoring points. We've got some other ideas of trying to further that development. I was talking with one of my geologists in the field about this week, and he had a fantastic idea that I'm going to pose to the team and see if we want to try it on a future project.
Great. I think this question is related to or specific to the case study you presented. This question is, have you encountered unexpected voids in karst during treatment?
Yes, we've actually encountered on a couple of sites. Usually it's identified during the upfront RDC phase. I can think of one site we completed just recently here locally in the central part of the United States, that a extremely large cavern type karst flow path was identified in a domestic water well region of the state. And boreholes kept collapsing, filling in with sediment or other things like that. And then surrounding wells that were present within the formation, depending on where water was within that conduit feature, would have a significant positive or negative pressure at the borehole head that was enough to blow hats off or cause significant sound when standing close to it. So that's one I can think of off the top of my head recently. But the cross-sectional view that Derek talked about earlier with the that showed the transport zone had a singular identified conduit pathway within that lower borehole that was utilized as the primary transport path for contaminant present within that lower area. So it is uncommon to find larger voids or cavern features when drilling, but it's less common than we historically see.
All right, I think we have time for one last question, and I'll field this one, Bill, since you've handled a number of these. So the question is, how do you use feature characterization and target fracture identification to in your plan to distribute amendment across targeted intervals? So this is a big picture question, right? So this ties together last week and this week. Starting with the RDC that Bill and I mentioned, we're looking at identifying those intervals initially through borehole geophysics, subsequently using a discrete interval straddle packer setup to sample, if it's possible to collect water at that interval. Usually it is. Sending that sample off to RPI's lab in Golden, Colorado. They run the analysis on it that we require for our calculations. We go through that calculation process, and then we look holistically at the fracture network, the distribution theoretically across the site within that network, and then calculate loadings for each of those features, fractures. If there's a zone, again, secondary porosity, a contact that we want to target that we have now shown that contaminant mass resides in, we have a calculated estimate for that interval. And then we look at how far apart our boreholes are, and we can start to calculate an aperture size that we need to, again, going back to what Bill said a second ago, determine the ROI for, which we can do and make those adjustments on the fly in the field. So there is a lot of upfront characterization, design, and assessment. But then when you get into the field, it also becomes a little bit of an art as well. It comes from experience. It's reading output pressures in the freshwater test. It's reading the system and output pressures during injection. Sometimes it's even visual. Bill had a slide up from a site, I believe it was in Connecticut. That site there, I think our estimates for ROI at most of the intervals were 50 to 60 feet between boreholes. And we know at that site that we got almost 130 feet because it started to weep out of that contact zone along a road cut there. So we actually had someone monitor that because we didn't want to continue to propagate product out of that zone. So, this is really it's a big picture, right? Fractured bedrock. We're not trying to say this is a simple solution, but we're also not trying to say it's very complex. I actually liked Bill's case study a lot because it shows that not just sustained treatment through the reagent, but by targeting its emplacement, it favors that sustainability of the treatment system in the subsurface over long periods of time. And you only get that by accurately targeting zones, getting the right loadings for those specific zones, and then knowing if in the future, again, setting expectations up front in the RDC, will we need to potentially in the future, depending on the size of the site, come back and augment this? Sometimes that's not always a clear-cut question. So we want to set expectations with you, our client, with the regulatory body you're working with, and understand what the future steps may be. It may not just be monitoring. If we're doing a pilot, how long are we going to run that pilot to assess efficacy? Are we going to phase this in? I have a site here locally in Philadelphia where it's going to be a 3-step phase. We're going to move out of the source zone into the central part of the plume over the course of 3 phases. So I do hope that we had a chance to address your questions here. If you didn't, obviously our contact information is in front of you. Please feel free to reach out. There are a couple very specific questions here in the chat. We'll reach out to those individuals here after the presentation within the next couple of days. A number of us are out in the field this week, so I apologize if it takes us into next week to answer those questions, but we will get back.